Okay, so hello community. I am Vedang Lokhande, and this is my presentation on celestial coordinates and constellations. In in Google Earth Pro, I tried to make a KML for plotting some constellations or viewing a galaxy, and I had some problems converting the celestial coordinates. Those are given here below to latitudes and longitudes that we use in KML. So this is a Crab Nebula in Google Earth Pro. You can see this by going in Google Earth Pro and going in the sky view and then selecting this. You can see right down here it says RA, DEC, and some arc degrees. So these are celestial coordinates first of all, and in KML you need to convert these celestial coordinates to terrestrial coordinates. So in this presentation, I'll go through what needs to be done to convert this and the concept behind using celestial coordinates. Okay, so let's give a brief overview of terrestrial coordinates that we use on Earth. So some major things here are the equator, this line that goes from here, and the Greenwich meridian that passes through London. We have latitudes from 0 to 90 degrees and longitudes. These are the lines that go from 0 to, I guess, 360 degrees or 0 to 180 in both direction. Okay. Here, okay. So it is a geographical coordinate system that defines location on Earth. We use latitudes and longitudes. Okay. So, celestial coordinate system is a framework used to define the position of celestial objects on the celestial sphere. So, celestial sphere is like a sphere of space, and we assume Earth is at the center. So, first of all, I'll read it and then I'll explain. The Earth remains, so the key assumptions are the Earth remains stationary while the celestial bodies rotate around it in a predictable way. So assume there's a huge sphere, black sphere, and Earth is at the center, and Earth is actually not moving. We are assuming this, and then we project entire universe on the outer sphere, that the black sphere, celestial sphere. Celestial sphere. Celestial objects are imagined to lie on the inner surface of an infinitely large hollow sphere with Earth at its center. So that's what I explained now. So we had like an equator when we were using terrestrial coordinate system. Now we'll have to do something that is similar to that. Here the Earth is at the center. This is the normal equator. We have a North Pole and a South Pole. Okay, and the North Pole is zenith. We call zenith the topmost point for an observer, and South Pole is nadir. You can look it up about more information about this. Okay, so vernal equinox, the zeroth point for celestial longitude, is the vernal equinox, which is intersection of elliptical and celestial equator near the point where red and green line intersect. Okay, so first of all, the red line which you see is the path that sun follows. Okay, so we are assuming sun follows a path, this elliptical path. Okay, and the position of sun during March 21st is recorded as vernal equinox. Okay, so the position at sun here intersects with our imaginary equator, and there would be one more intersection at the backside that we will call autumnal equinox. Okay, so 2 points: vernal equinox and autumnal equinox. So this point here is quite important, and using those points we'll calculate our RA and DEC. So RA is right ascension and DEC is declination. So The vernal equinox is this point. The back one is autumnal equinox. This is the elliptic celestial equator. The pink dotted line is the celestial equator, north and south poles. Say we have a point around here, then we calculate its declination as degrees from celestial equator. I'll go back once. See this star? So degrees from celestial equator, you can say this light green part. This will be our declination. Okay, and our right ascension would be how much does it go east from vernal equinox. Okay, so in latitude and longitude, it's similar to latitude and longitude. You go east and you go north, something like that. Right ascension means you go eastward, right? RIGHT, right? Okay. So that is how you get celestial coordinates of any star. Okay. Let's say now you have those celestial coordinates of the star, and now you want to convert it to terrestrial coordinates. Okay. Because KML doesn't support celestial coordinates, you'll have to convert them to terrestrial coordinates. So let's say you have some point, you convert that point and you enter that in your camel. So I'll explain the code shortly. So in the first line, you can see hint target equal to sky. So that we open Google Earth Pro in Sky View, and in Sky View we can see all the stars and constellations and galaxies. Then we have a balloon. It's a style. It has a name and a description. Crab Nebula description. Then we have longitude, a latitude, and altitude. Altitude is the point where you want to, put your object. Range is, like it's quite big, and you'll have to zoom in a bit. So range gives you the point where you want the camera to point to, like how much area should be visible uh, when we go to that point in our camera. Tilt and heading is for again controlling our camera, and these are the coordinates that you put again. It's a place mark, I guess. So this KML actually looks like this. Okay, so we have this KML. So RA, right ascension, D is declination. First of all, you convert this to the terrestrial coordinates, and this is the zoom. It depends on how much you zoom your camera. Okay. Okay, so now we'll do a hands-on for a constellation of Canis Minor. You can Google it, and Canis Minor is made of, I think it's the smallest constellation. I mean, the one with the smallest stars. It is made from Procyon and Gometia. Pardon me if I'm pronouncing it wrong. Let's go to the tutorial. So it should look something like this: one star, the other star, and an image overlay. Okay. Okay. So here is some resources that you can see. This is the KML Sky data. You can find the documentation for KML in Sky at googledeveloper.com. Okay. So in Sky mode, you have a tag called hint tag. So if you put hint equal to Sky mode, so it will understand that it has to open this KML in Sky mode and not Earth mode. Uh, you can say this hint attribute here. They have also given some explanation about conversion of ascension coordinates, right ascension and declination coordinates. You can use this formula. Then next comes the range. It looks quite complex, so we'll go into this by step, one by one. So this is the center of Earth. Think you can see my cursor. and this is the celestial sphere. Now, beta is the arc decrease that you see at the bottom of your Google Earth Pro. R is the capital R would be the radius of celestial sphere. I think it should be constant. Yes, it's given to us constant. So R range, I would say, is what you want to input in your code. So you calculate small r from this equation. Again, some things are constant and you are given, and that is given to you. Calculate that r and put that in your code. These are some standard r values that are calculated by them, like Sunflower Galaxy, Owl Nebula. I don't know how to pronounce them, but okay. And that's it, I guess. This is the code. I have also put this in my PPT. The coordinates and see like the latitude, longitude, range, how much zoom you want. Okay, and this is the Crab Nebula. Uh, I guess that is the only documentation I could find on the web regarding IKML. If you do find something more, okay, so now we'll make a Canis Minor constellation. It looks like a dog and it has two stars, something like this, two stars. And the two stars are Procyon and Beta Canis Minor. So this is the list of stars, Procyon and Beta Canis Minor. These are the prominent stars in this constellation. So first of all, um, we'll convert this to latitude and longitude terrestrial coordinate system. So and then we'll put it in our KML. So for Procyon and Beta Canis Minor, we'll do it the same. First of all, I'll show you the code. So starting with, we have two stars. So I have used an icon tag, and this is a star, a white color star. You can see this white color star over here. So I have used an icon tag for this. Next comes the image overlay. Just to make it more visually appealing, I have put a dog depicting Canis Minor constellation. I'll come back to how I gave these coordinates later on, and also the rotation. So first of all, what we do is we pin the location of the stars we want. Okay, and then we first of all we put the stars, and then we make a line between them. So the first star is Procyon. We get its address from Wikipedia. Then we go to Google Earth Pro. We search it. Okay. Then we select location picker and we get the latitude as 5.2 and longitude as minus 65. Okay. So 5.22 and minus 65. Similarly, uh, we do it for Gometia, that is the beta canis minors. And here we put a white star icon that we had initially uh, described. Okay, so let's do the same for beta canis minor. Then you put a place mark picker. It shows 8.2 and minus 68. So 8.2 and minus 68.2. So this is the second star. Okay, You can see I have taken the coordinates from Wikipedia star list, and I didn't find any website for direct conversion of this um, of this format from heavenly coordinates to terrestrial. So I prefer to directly put them in Google Earth Pro and using location picker to get the latitudes and longitudes, and not calculating them with the formula given. It's as per your choice. It also feels more intuitive if you can see the information about star that is available, um, and then you pick it up. Okay, so then we fill the latitudes and longitude for second star. Then we draw a line, a basic line. So the line style tag is used here. There are more style tags. You can look it up, like I guess the ring tag and rectangle tag. I'm not sure about it. So yeah, the width and then coordinates. These are the exact coordinates of the two stars, and it connects the two lines. Altitude mode, absolute refers to how you want the line to be clipped on your Google Earth Pro globe. So there would be, I guess, around four modes. First is absolute. Second is clamped. Third is clamped relative. I'm not sure about the fourth, but you can search it up. And the last thing we'll do is we'll overlay an image as well. So I have downloaded this Canis Minor web app from a source. Okay, and you give its href to be in the same directory. The color here I have done, um, like I have made this a little bit transparent so it doesn't interfere much with other stars. Then for calculating these coordinates, there's something I like to tell. Just a second. Okay. So as you can see, I want the image. Just a second. So I want the image spread across these two stars. But what happens if I put these two stars as my place mark for the image? If I do the later version, the image shrinks down, and the two diagonals of the image would be the stars, and that actually doesn't look well. So what you'll have to do is you'll have to do some hit and trial, and probably do a place mark around here and here, so that you get these stars aligned however you want. First of all, as I was trying for the two stars to be here and here, but that didn't quite work well, as the image broke down, stretched a bit. Then north, south, east, west. It refers to the north boundary, south boundary, as in north, how much right ascension I want. Just a minute. So, like, how much latitude I want for the north and south borders, that would be the latitude, and east and west would be the longitude. So, the boundaries, uh, longitudinal boundaries correspond to east and west. Then the last one would be rotation. So originally it would be horizontal, but I have given it minus 20 degrees rotation. You can do hit and trial to look it up, and that's how you make this. One problem I found about this was whenever I zoom out more than 15 arc decrease, the line or image vanishes. But in the previous version of Google Sky Data, I'd like to show you. So in the previous versions of KML in Sky Data, you can actually see the constellations from a zoomed out point of view. So the camera is too zoomed off, and still you can see the constellation. And this has changed in recent versions, I believe. Okay. Okay. Now let's have some fun facts for constellations. There are 88 officially recognized constellations, out of which the biggest one is Hydra, that gets over 3% of night sky view. Hydra is like a snake. Okay, I guess a Chinese snake. I'm not sure. And then Canis Major contains the brightest star in the celestial heavens, namely Sirius. So the image here is Canis Major. This is the brightest star there. Yes, and some other facts. The constellations we see depends on the time of year we are seeing. So during fall, we see Pegasus and Andromeda. During summer, we see Sagittarius, Lyra, and Hercules. During spring, we see Leo and Virgo. During winter, we see Orion and Canis Major. Okay. Now let's do a DIY. You guys try to get the stars coordinates of this and try to make a constellation. Ursa Minor, Ursa Minor. So the stars are like Polaris and six other stars. I'll not spell them. Okay, and that's it for the technical presentation. Thank you, and I'll answer any queries that you have in the chat. Thank you.